पपड़िया साहब स्टार्ट करें या शुड वी वेट सर?
If you permit, we shall start the session.
So I'd like to welcome Papadia Saab, President IGS, and so many other designations attached with him. So today I will not take time for that. So I also welcome Shiv Kumar Saab, expert faculty, and all my friends participants. So now I request our President Papadia Saab, sir, you can just start.
Surely. So our today's session is on a very interesting subject: failure of reinforced soil walls, lessons and remedies. So our today's speaker is Professor G.L. Sivakumar Babu. He is professor at IISc Bangalore, a very known figure in India in the field of geotechnical engineering. He has done his doctorate in the same subject from IISc Bangalore in 1991, and he has also bagged a German fellowship. He has also remained president of Indian Geotechnical Society for 3 years. He has also led the ASCE in India, and he has guided 23 research degrees, 18 PhDs and 5 masters. He has also authored a book on the geosynthetics. He has edited several books and papers. He has reviewed so many papers. He has bagged several awards, including John Booker Award from ISE MAG, Humboldt Fellowship from Germany, and his name is a milestone personality in the field of geotechnical engineering. So we are expecting a lot from this presentation today, and my request and invitation to Professor Babu to kindly initiate his presentation. I'm sure that we shall have a lot of interest and gaining of knowledge from this presentation. We are waiting for valuable net takeaways. Professor G.L. Sivakumar Babu.
Thank you, Sri Vivek Ji, and it is an honor and a pleasure to give some sorry, a lecture before this august community and under the auspice of the International Geosynthetic Society India chapter, because I think the failure of reinforced soil walls is something that is bothering in India, and yours is a forum under which we can discuss. Though I was discussing this earlier, but then I thought this is the forum under which you can discuss, and maybe if all of us agree, submit a report to the government with all our experts like Professor G.V. Rao and others that, of course, they have been working a lot, but at the same time, the things are quite challenging. So with this, I would like to start. And I should just mention that, this has been, when we look at the reinforced soil walls and its failures, it's quite complex. So in this connection, I had discussions with a number of experts. It's not only my work, and sometimes we had discussions with companies because we supply the products, and engineers, they just do quality control and all of that. So I just because this is a more simpler training program type of thing, I just want to give a brief introduction and also take you to what exactly are the failures and all of that. We all know that the reinforced soil technique was introduced by Henry Vidal, and in 1966, and its impact has been phenomenal in the infrastructure, and it has been outstanding, and we have seen a lot of construction techniques and all of that. Because of that, we see because we are going for a regular reinforced soil retaining walls, but then now we have a reinforced soil wall. The reinforcement is coming from geosynthetics and the facing element, and we have different types of facing elements. You have a concrete facing element, modular blocks, then gabion walls, and varieties of systems we have. And in fact, in certain cases, to increase the stiffness of the whole structure, we even have a secondary reinforcement. Then some sort of, if you want to, this is quite common nowadays. Has been, with tight reinforcing an element in the form of nails. You have some sort of system here. So there are a lot of things that we have been working on, and we also saw a lot of failures. This is the poor construction practice. You see that all the facing panels have come out, and the geogrid elements are exposed. And here you can see that again the reinforced soil and the steel reinforcement is exposed here, and you can see the kind of bulging and the kind of finish that they have. And this is another type where the drainage at the top of the wall itself is not good, and it led to problems at the bottom. General understanding was that there are a lot of why are these failures happening? Now there are different parties working here. You have a owner, you have a designer, you have a many others, consultant, manufacturers. So all of these people are there, and there's a lot of changes taking place. And what is happening is that some of the reasons that I just listed here. One is a lack of understanding of the design principles and quality control. Why there are some problems here. Then poor connection design. In fact, I said there is a reinforcement and it should be connected facing, and there is a connection issue. You have seen that there are some facing panels that have come out. Then the backfill quality that is so important has not been satisfactorily done. Then the drainage, that we have, we need to provide for the system is not satisfactory. Of course, the total quality control in the whole system is another issue, and a lot of communication gaps among engineers, contractors, and material suppliers is all of that. This is what we see. And so the issue is that when the technique has been so popular in the country, and at the same time there are a couple of failures. Why is that? That's what we'll examine here. Let me just come up with the studies by Turner, who is actually the father of geosynthetics in the whole world. He has been a champion in this area, and he says that he did a lot of survey on the geosynthetic reinforcement structures, particularly retaining walls, and he says that when you looked at more than 100,000 MSC walls, he estimates that there is about 2 to 3% or 4% failures, which is a big number. 1% or 2% is something big number, even in other places. I'm sure that maybe we are in the same range or maybe bigger, because the thing is we see that. But I want to tell you that in civil engineering practice, we have this understanding. How many structures are subjected to failure? Say, for example, Professor Vivek will be knowing, particularly in the dams, per annual probability of failure, they call it 1 into 10 power of minus 4. In fact, if you want to design a dam, you have to design for 10 power of minus 3 to minus 4 per annum probability of failure. Like, we don't want to see dam failure, right? So this is actually well recorded, and high cold and all of people are using. So this is based on 1 in 1,000 or something. So, but then you can see that it is much higher in our case in RE walls. So, and not only that, this criteria is being followed in most of the cases. So why not we in RE walls? That's one important thing that we see. And he had a database of 301 failure cases, in which about 94 are from excessive, the 207 are total collapse, okay? And then the 31 are excessive deformation. Because the reinforced soil is a flexible structure, and it has, there is a deformation tolerance, but at the same time, the deformation is beyond what is permissible. When you are trying to look at, failure mechanisms, all of the 301 or whatever number, he is even trying to categorize why is that? When you have, there are two things that when you are trying to look at stability, one is external stability and internal stability, right? So when you, in the 300 numbers, the internal stability, like when there is a, the reinforcement issues are there. So that is because it constitutes about 22%. Soil, why? Because is that, the friction between the soil and reinforcement may not be adequate. Actually, low soil friction. The soil friction itself is low, and then the interface soil friction is also low. Wide spacing of the materials, like so there should be something reasonably, you may have a design, but at the same time, certain constructional considerations, we need to have proper spacing here. Then the length of the reinforcement and also the wrong orientation, that I will give an example, some of them here, particularly the wrong orientation with the case study in years. That is internal stability, and the external stability, like what we use it for regular retaining walls, like over slidings, bearing capacity, and overturning, and all of them. So there are failures because of high surcharge, low soil strength, bearing capacity being low, steep exit angle, okay, of the then seismic forces, internal water, internal water. What is that? The thing is that, okay, the backfill, the wall fill gets whatever is that reinforced soil wall. It has it's because of the rainwater, there could be a problem. So the drainage is not sufficient. There is a catch basin leakage. There is a pressure pipe breakage, purged water, some restored saturated backfill, or even external water. Retained soil seepage. I showed one of some figures. Tension cracks, like you suppose you have some cracks at the bottom, top. There could be additional pressures, surface infiltration, phreatic line, soil erosion. This is all something that we have seen. There is a need to understand and come out with some plan to reduce this number of failures in India. And so of course, anywhere in the world, it's quite appropriate. And I was just trying to see what are the typical reasons for the failure of the reinforced soil structures. That what I did was that I put a questionnaire to some group of people who were constructing. In fact, they're all the members of the IGS. Say, for example, Mecca, then Strata, and all of these people. And I was in touch with them. And then they came out. I asked them, what are these typical reasons for the failure of flying rhythm that your organization handle? Because they have been advocating, they have been, it is the bread and butter, but still they had some failures. I was asking them that what are the typical reasons, what can be done to reduce the number of failures, because this is what is important for us. And what do you think about the IRC provisions, railways, the user? So do you see any modification? This is some questions that we have. And I just had some discussions. Then I can the contents. So I just made it's like a critical some failures I showed. Then the contents, what I just want to tell you would be that let us understand the principle of reinforced soil and its design, and what are the factors affecting the behavior of reinforced soil, case studies of failure and analysis, and discussion way forward with some conclusions. That's thing. When it comes to our retaining walls, we're used to in the classes cantilever, the gravity, and braced. They're called externally stabilized, in which you have a retaining wall, and it is a gravity wall. The weight of the retaining wall takes care of the force acting on the system. Whereas here, the bending moment and shear force, and this is again external stacking and all of that. As opposed to this, we have internally stabilized systems where you have a reinforced soil wall, in which because of the friction between the soil and reinforcement, there is a resistance to shear. So as a result, you have the reinforced soil wall, you have the soil nail wall, you have tie-back systems, and all of that. And we all know the principle of reinforced soil. This is the origin in which it came. And like when there's an example that everybody shows that you have a soil that is there, and then you put some sheets of reinforcement and stand on it. You can stand here. So that way it increases the bearing capacity. This is a standard photo that I think maybe I'm not sure if Henry Vidal photo or whatever, but you can see that the reinforcement in soil or the sand helped in increasing the stability of this reinforced sand. That's the basic thing. So when it comes to the British the BS code, The reinforced soil is a general term which refers to the use of placed or in situ soil or other material in which tensile reinforcement act through the interface friction, bearing or other means to improve stability. So, as opposed to the idea, the understanding of this tensile reinforcement and interface friction came at that point, when Henry Vidal did this experiment with fine needles on the sand. When he was sitting on the beach, he had these fine needles, and then he inserted here, and the doctor wants to jump on it, and he plays, and he finds it amusing. And of course, Henry Vidal has more. He's much more surprised. He goes to the laboratory and then finds that it's interface friction that's responsible for this sort of behavior. And he goes back to the lab and then develops the reinforced soil design procedures. So when it comes to reinforced soil, you have reinforcing elements, like it can be a strip, it can be a grid or anything. Okay, and then the facing elements, because once you have this friction between the soil and reinforcement, you need to have some sort of facing element so that the soil is stored or contained in its place, so that it doesn't get eroded. Then you have the backfill soils. You have which is supposed to be the wall fill, we can call it in a technical terms, like sand, a good sand material, because when we say that there's a friction between the soil and reinforcement, we depend on the interface friction. So if the soil is good, like a sandy material, like for example, we take 2/3 of, if the friction angle is 30 or 40 degrees or 35 degrees, we take 2/3 like interface friction. So something like that we do. And so I just showed you that figure, that what is the principle of reinforced soil? That's what we should understand. Because I always find that when you talk to a structural engineer or another person, they get perplexed with this. See, that is where the communication gap exists. The structural engineers are quite proficient in structural engineering principles, but when it comes to understanding the reinforced soil, it is a problem. Like I have seen a lot of failures because of that, because they try to always balance between the length and the diameter of the reinforcement. If you look at it, I don't know if you have interacted, must have interacted, but here the principles are somewhat different, because I'll explain in a minute. Like you take an unreinforced soil, you apply a load, then it has a tendency for vertical deformation as well as horizontal deformation. But the moment I put a reinforcement, what happens is that there is a friction that gets developed on the surface of the reinforcement. It can be a simple sheet, even a paper. So you'll see that it stands better. Only thing is that so there is a less deformation, whether it is vertical is higher here, much less here. And then there is a small horizontal deformation also. But these deformations are required to generate the tensile force in the reinforcement. Okay, so this can just it will be intact till it is a sort of a new equilibrium for it. It's a new person with a lot of reinforcement, like a lot of injections and all of that. It's like that. So we try to explain the concept that, see, reinforced soil is better, but it can fail because if the load is more, or if the tensile force is higher, it can fail, because the moment the reinforcement cannot take any more load, because the tensile force can be because of the loading and all of that. And the other one is that pull-out failure. Okay, so it induces a sort of what we call pseudo-confining effect. Okay, so that's what we try to say, that I just mentioned that here you have a sort of confinement here, but then the advantage is that because it's not deforming, what it means is that there is a lesser horizontal deformation or horizontal confining stress is acting. That's why there is a less deformation, less horizontal confining deformation, less vertical deformation, all of that. Why? Because we assume that there is the pseudo confining pressure is there. Okay, there is some mark here. Can somebody erase it or something? I don't know. Okay, so the mechanisms are that, suppose you have a slope, if an unreinforced slope, and at the same time, reinforcement, the possibility is that, as I just mentioned, because of the mechanisms that they have, it intersects the failure surface, like, yeah, let me just say, yeah, here. So the, how do you erase this mark? Can you help me? Somebody can help me? There is some mark that somebody has put in here. Okay, I can continue. So this is an example of a direct shear box we know. And then, we know that if a normal stress is applied, shear stress is applied, it's what we find is shear stress is nothing but PV tan phi. Okay. And but then if you have a reinforcement there, what happens is that this reinforcement, there is a friction. So you have a reinforcement developed because of this sort of arrangement here. Okay. And so the shear resistance is reduced, and the normal force, there is actually a vertical force. So if you resolve, there is a tensile force PR. So PR cos theta is a vertical confining stress added. It is increasing normal stress always better stability. And then you also have shear resistances reduced. So the advantage is that normally in the pure soil, we have only shear force is only PV tan phi. Now the increase in shear force is PR cos theta tan phi. The tan phi is a fixed angle of the soil, theta is inclination all along. This is a simple thing. So this is an example that we have that if you have the in a reinforced soil, the friction angle is 30, 40, it can be whatever. And the orientation, say for example, I just showed you that this angle here, you can see that the reinforcement angle is about, for the failure surface, in the range of 30 to 40 degrees. And even it can be 50, 60, there is no problem. And then even the same thing happens in the bearing capacity problem, slope stability problem, and many of the, wherever there is a failure surface, if you put the reinforcement, it alters the forces and it increases the shear resistance. That's what is going to happen. And one beauty is that between 30 to 60 degrees, you can see that there is always that increase there. So it's not really sensitive, and it's very good for our geotechnical applications. That's what it means. And other thing that is important as a fundamental principle is that because we are using geogrids, steel reinforcement, and all sorts of materials, so you have, we can call in terms of the flexible reinforcement like a geotextile or a geogrid, or a stiff like a stiff reinforcement. Okay. So this is actually stress strain response of a material, which is a reinforcement material. Then now once you put a sand backfill material, so it should be compacted properly. Okay, that's what the main problem in most of these RE wall failures is, that if you don't compact it, I'll just show you some examples that the compaction is a very, very important thing in geotechnical engineering. Otherwise, it leads to a lot of problems. So I just mentioned about the effectiveness of the reinforcement. So if the soil is, the reinforcement is very stiff and the soil is very dense, then it is very good. Like, this is actually the strain that gets developed here. It is just the strain is very low. But if the material is loose, so for example, this is a loose material, and it is effective, but the material is flexible. Okay, so it will take more strain. So okay, it is okay. It's as long as it is safe. Like it could strain maybe some 2% or 1%, maybe it's 0.1% here. But that only tells you about the importance of information here. Just to highlight that the stress strain behavior of the reinforcement, and also the stress strain behavior of sand, type of sand, or is it a loose or dense, also matters in engineering practice. Okay. So what are the factors that influence in the reinforced soil? What I just showed you was the explanation that the reinforced soil principle is this, that if you have a reinforcement in soil, it increases its shear resistance. Because soil is poor in shear, it increases the shear resistance by giving additional confining stress. It also reduces the shear forces that are causing shear. So it's a very nice calculation one can make, but of course all the programs give. But when it comes to, that is the principle, it's fine. But when it tries to implement in the field, you should understand what are the factors that affect the performance of reinforced soil? One is like you take the reinforcement. It can be a form of the reinforcement, like as I said, you can even people are using fibers, you can be using the geogrid, anchors, bars, strips. Any type of reinforcement which has some can be used. Then the surface properties of the reinforcement are very important because through friction it is happening. Then the dimensions, like what. See, the thing is that you're trying to calculate the forces in the reinforcement, so dimensions are important. The strength. I just mentioned about the strength of the, I showed you the sustain curves. Then the stiffness. The strength and stiffness are very important. Like for the geogrid, it may be more flexible, but the strength is good. But in a reinforced soil, like for example, steel grade, the strength is good as well as stiffness is very good, very high. So there's the effect of so the proper choice of reinforcement is important. Then the reinforcement distribution. Like where should I put the reinforcement? Because you have to put wherever things are weak or wherever the stresses are maximum. Like so for example, if there is a loaded area, you have to put just close to the load so that the loads are coming on the reinforcement, so that the loads on the soil are less, so that the soil is okay. Then its orientation, I just mentioned that we have to stick on to that failure surfaces and then orientation. That fortunately in geotechnical engineering, it's very, very appropriate. Geogrades and geosynthetics are quite good. Spacing, right? Spacing is another issue, that what type of spacing, because you can't have a too wide spacing, you have to have a proper spacing. That is also dictated by the compaction, like you have how many lifts you have. What type of soil? So for example, as I said, soil particle size with the clay or a sand or gravel, or can we use? No, people have a lot of questions because that is a bulk material in reinforced soil construction. One important thing, I just tell you the difference between a structural engineer and a geotechnical engineer. See, the people should understand that it's a soil behavior that controls the whole thing. If the soil is a bulk material, it's a construction material. Okay. Then the grading, mineral content, and index properties, they're quite important. Okay. So the soil, the index properties, the type of soil, and all of that are there. Soil state, I just mentioned about the impact of the density. Like soil cannot be loose, so because it takes a lot of tissue, so you should have proper specifications for density. Then the overburden, like state of stress, either is a K0, Ka, and all of this. Degree of saturation is also important. Construction method, in the field, when you're trying to do that, the geometry of the structure, you have seen different types of facing elements, different type of systems that you have in the reinforced soil. There are so much innovations that are happening. Unless, like you have anchored, reinforced plus anchored soils and all that. Unless you understand the reinforced soil structure itself and their construction system, you will not be implementing it effectively. Of course, the people who are practicing, they know very well. As I said, compaction is important, particularly in the field. Construction system, the way that we construct, like facing elements. Then the aesthetics also matters, durability, all of this is important. So what are the elements of design? When you're trying to talk about, as I said, external stability is similar to what you do in regular retaining walls, like sliding, bearing, and overturning. And the internal stability, the internal stability is something that since you're putting the reinforcement, we should see that there is, it doesn't fade, like tensile spacing, tensile overstress we call it. Then the pullout, it should not come out. Reinforcement soil should not come, the reinforcement should not come out. Then the third one is the facing connection. When you're putting the reinforcement to connection, you connect it to the facing, it should not break there. These conditions we should take care in a simple way. So having understood some sort of design principles, like of course you can, like we actually, the way that we design is that, say for example, external stability, like we have the regular systems of sliding, we have retaining reinforced soil calculations here, 3 of them. To do that, they're all given codes. And then here we calculate in the internal stability, we calculate the, we assume earth pressure distribution, and then calculate the force coming on the reinforcement, and see that there is always a factor of safety of everywhere. Factor of safety with respect to tension and pullout is sufficiently okay. Even connections everywhere, the factors of safety are more than the those numbers specified in codes. That's what we do the design, but it doesn't happen, right? So what I will do is that, so we have seen many very good success that we see, all of us, all of us, we all around we see everywhere, but then there are a lot of failures as well. This is some example, that we did somewhere I saw with some time back. We have many, but I just want to, I don't want to show so many failures, but because we want to understand, just to have a sort of context for the lecture I'm just giving. Here, before it was open for traffic, all the facing panels have come out, and of course, then you can see the way that the loading is coming on the facing, which should not be there. This is just an example. Of course, there's a bulge and all of that. So there's another section here, like the geogrids are all now they have to be connected here, but then actually there is a failure here. So they have all come out. So what has happened in this case was that this is a type of connection that they have. It's actually a connection failure. So when you want to do a failure analysis, actually I worked on forensic geotechnical engineering. Okay, so we can't. There is a systematic method of doing it. So you have to understand and characterize distress. So make some, then you should do some diagnostic tests like backfill tests and geogrid samples, whatever. And then you have to understand why things sort of fail. You should develop what is called a failure hypothesis, and also check with design. Maybe you will, the moment you go to the site, you would generally have some reasons to say that this should have happened, because you have the background to understand what has gone wrong. Then you try to check up with actual calculations and reiterate everything, then come out with a failure hypothesis, then do actually real analysis using sometimes conventional methods. Say what I just mentioned for retaining wall, reinforced soil walls, you have a lot of design methods like the tie-back pressure method or the current gravity method, depending on the type of reinforcement and all of that. So even you have numerical methods, because numerical methods will give you a clear idea of the deformation. Because the reinforced soil is a deformation control, and if you want to understand deformations, you have to only do the numerical analysis. Then you give suggestions and specification for rehabilitation measures based on analysis. Okay. So what was the reason here was that the area experienced continuous rain, 4 days, right, continuously, and it led to damage to earthwork, damage near abutment, leading to misalignment of panels, which you have seen, and sand flow was noticed in some of the panels, like in between this. The height was particularly the longer, higher heights, late 8 overstressing of the connection resulting breakage of the grade and panel. That's what happened. Panels of the day. So what then we looked at all the calculations. Okay, shear strength of the soil was good, because you have seen the good sand material being used, compacted, everything is okay, and the permeability of the backfill also we measured. Okay, because that's I just mentioned to you that there's a lot of rain, right? So the rain was though the permeability of the backfill was good, the rate of infiltration during those 4 days was so high that it led to a flooding situation in most of the cases. Okay, because some places are unfinished, and actually it was about to be opened for traffic, and they have not put even a proper cover. Actually they must have put a plastic cover, would have really reduced they would have avoided the infiltration. And they thought, then somebody was blaming them that he used a geotextile here instead of the backfill. That led to that problem. Actually, that was not the problem, because the permeability was okay. The permittivity and other things seem to be okay. Like we have a habit of putting a geocomposite or a geosynthetic material next to facing. That was okay. But then the drainage, they have not put the drainage element, that 600 mm or whatever. So that was an issue there. So they were mentioning that was the reason, but when you look at the permeability, they look to be all right. Then other important thing that what we observed was that when there is so much of rain, as I said, there is flooding, there is the earth pressure will increase a lot, because we assuming sand, and then the drained friction angle of some 30 degrees or 32 degrees or something. There at coefficient of earth pressure we assume, then calculate the earth pressure, and then what should be registered by the reinforcement, all that we calculate. But then we have not accounted for the pore pressures. What happens if there's a lot of flooding continuously for 1 week. So that led to a small considerable increase in the reinforcement, and also panels could have tilting. Some places it has come up. Okay. Then there is also that the minor issues were there, that if you use in some places, we tend to use two varying types of glue grids too much, but the stress and characteristics will be marginally different. And if the soil compaction is also not good, that may lead to differential shear stresses and differential movements, marginal drift that can lead to some thing. And some remedial measures were suggested, but I think finally there was a problem with the failure. The second, this is another thing that we just recently did. It's again highway, in national highways or railways. Actually, it's a national highway 1, and all the facing panels come out, and you can see that there is a clay content little high. On it is not a bigger weight. You hardly see there are only 3 or 4 panels, 1, 2, 3 maybe. But then the kind of the whole of these photos were circulated throughout India and WhatsApp. Right? I remember that everywhere. All the groups in engineering, right? We are experts in WhatsApp circulation. So then you can see the type of soil here. So here again you can have the connection to design. I just show you. So there we're able to rehabilitate and all of that in some form. You can see 1, 2, 3, 4, 5 panels. We removed that one panel this side and repaired it. It was all right. Luckily, within 3 months it could be restored. What has happened here was that the type of soil itself, I just mentioned here, normally the soil investigations of the back indicate that the silt plus clay content is in the range of 28%, which is more than what is permissible, contributing to the settlement of the soil mass, which affected the integrity of the connections. In fact, even the connection quality was also not very, very satisfactory. That's what I understand. Anyway, I've seen that, but not tests for, we don't have any connection tests that they had performed or something, I'm not sure. So, but then we could essentially rehabilitate in no time. That was the issue, there is no problem. This is another confusing issue. Even now, the contractor abandoned the whole structure and more than 10 years now. And, you can see the bulge here, bulge. It is normally bulge, normally we have some certain limits there. But here it's about 400 mm, which is something very unusual. But the road is all at the top. The road is very good. Everything is fine. You don't see anything at the top, and people are using. They're happy with that. But when it comes to the sort of, actually what I showed, the 2 failures that I showed was more about the collapse failures. Like in reinforced soil, you have 2 types: deformation failures as well as collapse failure. Like I just gave some examples earlier. Similar to that, I just wanted to show some examples here. So here it is a lot of deformation, and of course somebody suggested you do soil nailing and all that, but it didn't really, it may have helped perhaps, but this is the way it is being done. You can see the outward bulge, it is quite high. It's a parking jump. So what exactly has happened here is that I have just explained to you about the strain compatibility diagram. Though there is a reinforcement, okay, so it needs some strain to develop reinforcement force. As the strain is increased, there is more force, right? Like that's what it happens, and it depends on if the soil is poor, then it will need more strain. If the friction angle is less, it will need more strain. Something my small changes will be there. So the what happens is that in this case, it's about 0.3%. If you want to say that, say, for example, here, this is all a good retaining. This is, you can see that here, this is actually stiffness of the soil, and this is good and poor. And about 0.3% will be a typical strain, D delta by H is a strain that gets developed. And so that deformation less than them are accepted, close to them are accepted because we need the force. But here it is much more. Okay. In fact, sometimes our code says that BS 8006 1% as the limit and the design load is sustained. So sometimes if you use a flexible reinforcement like geosynthetics, even 1% is okay. So the corresponding deformation in this for 10 meters about 400. In this case, about it's 40 centimeters, 40 centimeters, which is slightly higher, but it was all right. The strain levels are high. The deformations in this high range, but they have been constant for a very long time. People have noted, and I checked up all. But then maybe it is in equilibrium. It had deformed where maybe the type of soil is a little poor there, but then the compaction and even the type of reinforcement, low grade or something. But there are no other guesses on the payment. But so the high deformations what we felt was attributed to poor state of compaction, not too poor, but poor. So soil lading somebody is already used. So we just have to tell them that you have to be monitoring the structure, because though the deformations are not acceptable, but it's still working. So that's an interesting thing. This is another case that I just wanted to show. This is not a failure; it's a very good thing. It's a I just want to do a 42-meter high wall in a reinforced in Vijayawada. Okay, it's a 10.5 each side, and you can see a lot of traffic here. And at the top, this is essentially constructed to develop a parking place for the goddess temple at the top. And what happened was that you can see that this is a model block construction, and everything is fine. And they started putting the backfill and all that compaction, and they wanted to leave it to opening so that the paved traffic can come and so that people can straight away go to darshan or something. But then what happened was that we should know that the soil is reinforced soil, and we have a lot of soil element which is prone to settlements. So what happened was that there was a lot of deformations in the soil, particularly though, and then whatever is the pavement, the parking pavement that was laid started cracking, and people were so worried that it may fail. But finally, when we made all the calculations, this is the way it is. So the top area of the wall apparently explains considerable deformations leading to cracks in the area. The large settlements were a cause of worry. And then they were wondering, they may totally collapse. But then I said, let us look at it, because we have such a backfill. So much of backfill is there in this material, and it's prone to settlement. You can't put, it's not like a concrete thing. Like we start after curing it. After 28 days, you start doing another layer. Whatever construction you start. It's not like that. Soil, you have all of the deformations. I said you have to wait for 1 more year because the settlements are there. They're going to happen. You do not do that. So I suggested them that you just monitor the deformations, and then we measured them. They were in the range of like 1%. Just earlier we discussed in that same range of deformations, which are okay. And then you keep on filling it up and make sure that the deformations are constant, and then start using it. So they have to postpone everything by a year, and it was fine. So we made detailed analysis, and why it is some 3D analysis understanding was also made to some extent. Why because we normally make a 2D analysis and all of that. So finally, we could say that it is safe. What I meant was it's very good. Why? Because appropriate geotechnical interventions are required when you're trying to do right from the beginning to the end. So if geotechnical engineering is not there in the project, it could lead to some uncertainty, some issues of quality control and all of that. Okay, that's what I want. This is a good, very good case study. I just wanted to highlight some more, like This is from the literature. This is again a segmental wall. You can see all of that elements 1 to 45 or something. So small segments. So it has failed, during rainfall. That's a quite natural that we always see that. But why it happened? So the forensic analysis identified that the connection between the facing and reinforcement is a primary cause. This is one standard thing they mentioned. But the thing is, the pressures are because of the water, not because he may have assumed K gamma H or K naught gamma H as the pressure and then calculated the tensile force in the requirement. But he would not have assumed the effect of rainfall and all of that. Okay, so that was he may take only a drained friction angle in calculations. Okay, that's so. Then they used a software which has no consideration of the connection strength. Some people it depends on, like, you have to really make connection strength also. You have to calculate what is the force coming on the connection, because normally we assume that 60% or whatever some percent comes, and then connection design has to be proper. Okay, particularly when rain comes, there will be higher load coming and it fails. It's not because it's some other problem. So that's what happens here. So what they did was that, okay, the remediation included the removal of the wall face and reconstruction, increasing the connection capacity between the segmental concrete units, and reinforcement by a factor of 3. So as I said, I told you that the design steps, the tensile force, the pullout force, then the connection force, all of this needs to be properly evaluated and have proper factors of safety. And then they also made, and the reanalysis considered the storm detention structure. There was some, say, imagine we also have in India, most of the time there will be a drain here, and then if the rainwater enters the retaining wall, it is a problem, right? Sometimes this is where the seepage province need to be correct. So they have done that. And then they maybe proper lining, or you should not have proper gradient of the stormwater and all that structure and all that should be done. And then the toe bomb was also provided as a measure of abundant caution. This is from a Geotechnical journal, which is a very standard journal for all of us, right? This is another one interesting case study that the very recent again, we claim that we are constructing very big retaining walls and all of that. This is about 67 meter tall wall, too big, close to an airport runway, right? And it is failed in years. Both of them, what I showed is talking about failure. And then the reinforced soil stroke failure destroyed multiple homes. You can see that the road completely got washed away. I mean, a lot of problems it led to, and disrupted airport operations. And it led to a lot of problems that we can see that. Of course, they were looking at why the factor of safety, all of that. So you can see that the complete wall failure happened. So when you looked at why it happened, one thing was that insufficient geotechnical investigation, and then the interpretation of the data for design and detailing. Here, see, you know that in years there are experts in reinforced soil, and it has happened. I just you have from India and 2 cases from here, so nobody is above board. We need to work hard to see that the failures are reduced. So the 3D aspects, that's very interesting. That low load, I just told you about this point earlier in the factors of reinforced soil. So what happens is that the load that is coming is in a 3-dimensional movement. Okay, there is so much of load. It's a 67 meter high slope. On every geogrid that is expected to reinforce, there is a 3-dimensional load coming. But then it's reinforces uniaxial. It's not, the slope is not in the one single direction. It is actually in other directions as well. So they have not really addressed that point. Maybe they should have taken a good geotechs like bags, hill or tracks. We have no samples where there is a radial distribution of shear stresses there. Under insufficient foundation preparation, rock excavation, benching due to inadequate specifications, again at the bottom. Folding of the RSC soil and the compacted soil instead of the freshly excavated soil. Okay, so this is another issue. Like they didn't, this is a very serious thing, when at the bottom has to be the best, right? If there is an issue there, then that may lead to problems. So this is another important thing. Significantly shortening of the geogrid in the lower portion of the slope from, so they are also, cost cutting, right? Somebody did, I don't know why it is. Then deterioration of the soil rock interface strength from peak to the other thing that happens, what happens, see, when there is a soil and rock interface, okay, one should be very careful. I have seen a lot of slope failures because of that. Soil, it slides when the rainfall comes, the rainfall can enters, seeps through the interface and completely whole patch comes off. So I think we have to do proper geophysical studies and in fact connect the slope surface to the rock surface. We can't allow the shear forces to develop along the interfaces. So, and then it should be properly, there could be deterioration, but you should understand what is going to happen. So this again, I said about inappropriate testing and all of that. So there are a lot of other things like poor complete in design, no chimney, blanket drain, lack of peer review. These are sometimes, we also do. Constructability and lack of monitoring program, incomplete evaluation of observed tension crack. There was also tension crack. Okay. So these are all some things, So if you, in summary, what I should say is that you have connection failures, you have finite soils in backfill, you have compaction problems, you have internal drainage problems, you have surface and adjacent water control. Like, if somebody is doing something else somewhere, but it should not affect your structure. Then additional design issues. You just again see. So you must have seen that I just mentioned that the loads on the connection are the maximum tensile force that comes from reinforcement. And sometimes what happens in India, if the connection is not good and the soil close to that reinforcement is not compacted well, a lot of stress comes onto the connection joint, and it can be due to it may lead to additional moments, like not just so it can lead to issues. So it can tilt, and even we have seen the facing panels little tilted, right? So it's important to understand the important the connection position to avoid it. And so we should do connection tests, like you have to take some products. Nowadays, what is happening, mix and match, like they don't standardize products. So they just, so that's a problem. So connection failures need to be done properly, and field tests also, because you can't, if things go wrong, you can't even, like I just showed you, there are only 4 or 5 panels or 10 panels that has come out, but then the kind of image that as civil engineers we have, or particularly reinforced soil, we are promoting geosynthetic industry, and it is a problem for us. So we can't allow such. Clays people are using, there is nothing wrong in that, and IRC used some specifications for as it's 20%, more than 20% should not be used, but like we should be much more careful. There is nothing wrong in using that, but you should understand the clay behavior properly. Like in fact, there is a professor Barry Christopher, who wrote Federal Highway Guidelines. He says clearly that you have to understand the permeability. Even I showed you an example where the permeability of sand itself was not okay because there is so much of inundation because of the infiltration. So property like permeability, undrained shear strength, drain shear strength, stiffness characteristics. Stiffness, like as I said, stiffness, if the stiffness is less, settlements will be more. So you need to understand in the specification you have to give. I have never seen, with all due respect, for the backfill the complete information. So what is the soil? Some 3 or 4 pages. Take a backfill soil, give this compact it to the maximum dry density and whatever. Get the drain response. Then what is the stiffness? Then moisture density, all of this, then permeability, everything you measure and propose field specifications. Nothing is done. I don't know. This will say something. I never saw that specification document. Okay. So the density should the corresponding shall be evaluated and elaborated, and then the compaction lift thickness of 200 m should be followed, because our people dump it. See, because in the night, if you don't go, you don't know what is going to happen in the field. That leads to compaction control if it's not there, because compaction thickness alone ensures you proper density models. And backfill material close to facing needs to be properly compacted. Okay. And then there are also certain small tricks people trying to use, measures such as use of long reinforcements at the top, secondary reinforcement, provision of chimney drains, surface. Something you have to be much more extra cautious. And people tend to conclude that the geosynthetics are not very good in India, but then no. See, we don't understand, maybe there's a lot of muck, and then if you expect the geosynthetic material to behave in the presence of certain things, you have to understand properly the permeability behavior, geocomposite behavior, and all of that, and effectively promote the techniques. Drainage provisions are very, very important because as per federal highway, we have to say that drainage design has to be properly provided. One important thing that I want to say that our design documents, people generate documents, that luckily, unfortunately, the software generates generate document, right? Generate document and automatic print. Yes, but I think it's all tricky. See, I was just looking at one structure where you say the RE walls, they're supposed to have the British 120 years, 50 years, 100 years. There's a life associated with that. So you have to really design for 1 in 100 rainfall, and then you have to get idea of intensity relation relationships in the drainage basin and effect of seepage forces. If you don't study, what will happen? Definitely the forces will act on the rain. So you have to really do a proper drainage design. Otherwise, it's not correct, and it should be reported with the design documents. And then the provision of 600 versus geocomposite needs to be evaluated because of the IR specification. See, we have to evaluate site-specific design has to be given. It cannot be so much. It's not complicated because you have the rainfall data and all of these site conditions. Nobody gives that in any of the documents. Then that's what both drainage and filtration calculation need to be done as part of the design documents and appropriate gradations and filters. And even somebody will suggest some geosynthetic material, somebody will use that filter. I have never seen somebody using it properly because the client, like state government people or national, they don't know. So somebody, I got their sample. Did you know, is it useful? Nobody said for filtration. So of course, failures and filters are less. But at the same time, ineffective filters can have a lot of problems. So, it can lead to seepage and poor drain arrangement and all of that. Right? Yeah, see again, these are all, so these are typical structure, and we need to really have proper analysis of the system. Then only it's possible. This is what I was trying to show here. So, for example, you have a collection. See, the thing is, you are trying to put just now I showed you that, they put a compacted backfill here. So had to have a good drainage here, then a good water. So whatever is nothing should come to the backfill. Some other wall fill, you can say these are all wall fill. All the water that comes, you may even have a drainage, some sort of thing that can connect like this, so that the water gets collected. These are all known, and you have to calculate. You can't be arbitrary because how much of seepage will come and how much is the discharge that is come at the power. They're not. Very tough calculations. Now software programs are there, you can do it, but we can't allow failures. There are also a lot of additional people that always I come up with this question that some part of the olive is in the pile cap and the rest is on the soil. What should I do? Because it leads to different settlements. People have seen that. So you can have some sort of system here where they have so there are methods available for this. What I just want to tell you is that you have good people here in the section now. We need to document failures and lessons also to establish proper practices, because whether you learn, if you are able to learn something, teach to everybody. We have to have collective efforts. A categorization of clients. In fact, I'm so happy that we have Vic with who is the president of the main chapter, presiding over our meeting and all of that. So, we have to really look at, in each client, if they should maintain records, like if the NHI, if they don't have data on what failures occur, then it is difficult. Like, you go to a doctor and you should have your health record. It's like that. So construction observations and review of the field reports during construction need to be done by geotechnical engineers. Actually, The employment of the geotechnical engineers is not there. You have 1 or 2 persons working here and there for the whole project. The moment he runs here, somebody compaction is done badly there. We are seeing. See, the guidelines are available. NCMA guidelines. They clearly tell you the role of each of the persons. Like if there is a geotechnical person, this is his job. They clearly mentioned what is the role of a civil engineer, what is the role of a geotechnical engineer. But if you have only one person for the whole project and if he doesn't know much, then it's a problem. Some of the softwares you should be careful, but you have to understand all the problems. Inspection manuals and comprehensive lists are necessary from all the people. I think everybody should be on the same page when we are trying to do the work. It's an engineer, it's a contractor, it's a owner, because we can't allow failures. Thank you very much.
Thank you, Professor Babu. Very interesting case studies, and the solutions that you have proposed are also very interesting and very logically convincing as well. So, I'm now switching to the questionnaires, and some questions have come in the chat box, which I'm reading out. The first question is from Mr. Sanjeev. Most of the time you have mentioned that geosynthetic has not been used or not helping. Are you eliminating the use of geosynthetics by better drainage? Kindly help me understand. I think he has misunderstood. You are a better person to answer. Yeah, please.
I think he can happily talk to me. There is no problem with me. I think our whole purpose, as a civil engineer, geosynthetics is a boon for us as a civil engineer, whether you're a transportation engineer or highway engineer or structural engineer or geotechnical. It's a boon for us. So it is not to. You can come and then I will give you all the material, Mr. Sanjeev. It will be a pleasure. My lecture is only to convince that, that's what you, if you see failures, that's the thing. You have to go through a proper courses, and how to avoid failures is what we are discussing. And see, I also mentioned the failures also there everywhere. It's not unique only to India, they're everywhere. Even regular structures also fail. Like you must have seen road collapses everywhere, and we are not ashamed of them actually. Whenever there is a drain, it's a problem. We have. So I think you are welcome to discuss. That's what I could say too, because yes, sir.
Thank you, sir. Thank you.
Yeah. So
Sanjeev, you are the Sanjeev, sir. Yeah, tell me, sir. I'm happy to see you. You are welcome to talk to me anytime, sir. I'm happy to see you. I thought a young boy. I'm sorry, you are a senior person.
No, sorry. Actually, I'm sorry disappointing you for not being young, but of course,
no.
My knowledge is not as good as the old man.
No. You can come and say, you can start anything anytime. That is now condition. You are welcome. I'm very happy.
Thank you very much, sir. Thanks a lot.
Yeah.
So I would request all to kindly type down their questions, if any.
So for all of the geosynthetic functions, they're so helpful. They're multi-dimensional. So we are so lucky. You have the same material for reinforcement, drainage, filtration. What the very is that? We can't do that. No, I can't do. Any material cannot do that. Steel cannot do reinforcement, and then nothing can do that. Same two functions.
Compaction is a big issue. So that is number one. Number two is, the allowable strain in every reinforcement is of a different level.
Yeah.
The topic that you touched today, that we use sometimes the unilateral or uniaxial kind of a reinforcement, but the strain is not possible to be limited to be uniaxial because of the warping effect in the soil, that there is two-dimensional strain in the reinforcement that is actually required, but our idealization is only for uniaxial. So because of our wrong idealization, that the reinforcement is unnecessarily strained. But another is the aspect that the limiting value of the strain at the design level is also not duly honored. Yeah. And that's why in the field, the actual strain is much beyond the limiting value. So my fundamental suggestion here is that can't we develop a design methodology with limit state approach into the geosynthetics, especially the grids and the uniaxial grids, biaxial and the uniaxial grids, so that the limiting values could be duly honored with the due factor of safety.
Yeah, actually, see, as far as the limit state design is concerned, it is unfortunately in India, IRC also they have not done. Okay, because all bridge foundations and all they have to be LRFD, lower resistance factor LRFD approach. And in that process, there is also a possibility to consider strain levels apart from allowable stress levels. So I somehow even they are not attempting. I don't understand. It is a straightforward question. It's not a problem of the understanding every small issue and then allowing it not to reach its limit. Yeah, I think so. So there is some question that has come.
Yes, this question is from Dola Rai Chaudhary.
Oh yeah. My friend, great. Yeah, in the
Yes,
we are observing sometimes
another yeah, so she has typed like these. Another distributing trend we are observing, disturbing trend we are observing in some sites these days is different types of geosynthetic material used in the same structure at construction stage, that is after design, which may have different strain characteristics. The behavior of such structures becomes very difficult to predict.
Absolutely. Actually, she has a lot of experience. I know. Yeah, I agree with her. That is a problem. No, see, we don't plan well, understand the behavior. We have never said we are in a hurry. Whereas in abroad, it doesn't happen. You try to understand everything. Everybody is on the same page. What is being done, either contractor, manufacturer, supply, or whoever you have, and they understand their work. The journey is together. It's a journey together. It's not, and then that way the failures are less. Otherwise, even one thing is not there. And I find it's this. I mean, I agree with Madam actually. Yeah. If you want to add anything, she can say, "Oh, Dr. Balan is there."
Yes, another question is there here from Muhibuddin Qazi. Sir, the IRC SP102 mentions both tieback wedge method and the coherent gravity methods for different types of reinforcements. In FSWA NHI 10024, simplified coherent gravity method is applicable to both geosynthetic and metallic reinforcements. However, BS code specifies tieback wedge method only for extensible reinforcements. Can you share some highlight on the differences?
Yeah. So my own take on that is that we know that for use the current gravity method because the people found an economic advantage by using the current gravity method. They developed, but in fact there is a nice paper by Professor Jones, Colin Jones, who is an authority in soil, and there are assumptions there. So this it takes care of things and whatever. And that is somewhat empirical. So current that is somewhat empirical. Oh, how much important is to collect soil data before designing? Oh, it is very, very important. Yeah, I mean, so the issue is that it is the most important till even you have to collect all the information till the project is completed also. We don't know. Like we have to understand how the soil data has been helpful in better performance of the structure. It is like right from investigation to backfill characterization to wall fill characterization. All it should be like I was just mentioning. It is not just characterization in a simple sense. The strength, like everybody, I think the madam was also mentioning about stiffness, strength, and all. You have to come out with specifications. Like very Christopher says, very nicely. Use of fine-grained soils they want, but if you don't have proper specifications of strength and stiffness in drained and undrained conditions and permeability numbers, then we are wrong. We can even measure them. See, if there is a leakage, you need automatically back calculate permeability. There is something wrong. You can calculate. Our structures are not complicated, easy to analyze. Okay.
Another is the question, what are the soil stability analysis methods before placing or laying geosynthetics or geotextile?
You mean the ground improvement is asking? I'm not sure. But, before placing. Yeah, actually, see, if it is just, it looks like, the compaction is a number one important issue, but, I don't know what he is referring to here. If you want, you can say openly. But see, we need good interaction properties. So we need the soil analysis is supposed to consider both the soil properties as well as reinforcement properties and give you the improved numbers, whether it is a geosynthetic or geotextile. And we have methods also. Okay, there are a lot of methods. If you want, you can talk to any of us, like Professor Bala and any of us, who is fascinated with geosynthetics, we can tell you. Okay.
Another is the question, sometimes it is not possible to comply soil properties according to codal guidelines, like free draining reinforcement fill, there is 530° or fines content less than 15% as per site restrictions. My personal observation is we need to modify code with different types of soil combination.
This is actually, as I said, he rightly said personal opinion. Okay, that let it be there, because it's not easy. Like, we are struggling, and let us not dilute any standards. And maybe, say, for example, you have used flash, you have used some other material which has reasonably equivalent properties, but because again, we like even Madam was mentioning, you can't mix up. Too many mixing up will be leading to dangerous things. Compact mixture was not good. If you add some more 2 to 3 types of soils, their properties are not. Actually, quality is number one. If that is an issue, then we can do anything. It's not a clay soil as such is not bad. But how do you come up with, see, the reasonable, in fact, zones, there is a lot of work done on this. See, some clay soils, sometimes they may be better also, but as long as they have a strength and stiffness, and minimum all that, it is not difficult, but we have to be site specific. Somebody like, this should be a systematic work. Yeah, that's what I mean.
Any other questions, please?
Yeah, I have a lot of my friends here. Just now myself and Anil and Dixit came out of one meeting and I came to lecture here. Yeah, with the Navy. Jimmy is here. Yeah, we actually, Jimmy developed, he was, he gave a lot of inputs to the thing. I think he was more information.
So I think there is no question now onward. So I'm really grateful to Professor Babu to have shared with us a vast knowledge base that you have gained out of your academics and your experience both. And we all are much grateful, feeling enlightened by your construction monitoring requirement have also been duly underlined by you. So it was really speak very enlightening session today. And I'm sure that, our construction habits will be continuously getting regalvanized by these kind of deliberations. eye-opening deliberations. So again, I'm extremely thankful to you and the CBIP for providing us a platform to organize a very nice technical talk, Professor Babu. Thank you to
Thank you,
all.
sir. Thank you, sir. Thank you so much. Thank you. Thank you to everybody.
Thank you, sir.
Thank you. Anil.
Thank you.
Thank you, sir. Thank you very much.
So I'll take leave.
Pietampuर में